Alrighty, everyone. So for today's lesson, we are going to be looking at ionic and net ionic equations. So this is really just taking what we've already been doing just a step further with our modeling of our double replacement reactions in particular. Net ionic and ionic equations are just not useful at all, really, for single replacement reactions. So this is really just focusing on those double replacement reactions. So if we look at a simple reaction, silver nitrate plus calcium, or not calcium, I'm sorry, potassium chloride, we see that, we make solid silver chloride and keep some aqueous potassium nitrate. So the big question here is what's really going on in that solution? That's what we're trying to get at. And so one way we've used already is to show a beaker model, to say, hey, look what's going on. We see before the reaction takes place, all those ions are just floating around in solution, and after it happens, that silver chloride is a solid, it drops out, and the other ones are still just floating around in solution. So do me a favor really quick and put on your kind of algebra brain and think, if this were an algebra problem, what would you do if this was an equation and the arrow was an equal sign and the junk in the beaker on the left was the left-hand side of the equation and the junk in the beaker on the right was the right-hand side of the equation? Hopefully you're thinking, well, gosh, I would simplify because I have floating around in both sides of that equation a blue dot and a red dot, right? They never do anything different. So what we end up looking at, right, is we want to really look at which ions are actually involved in the reaction, because just like with algebra, if you cancel out all the extra crap that's not doing anything, it's kind of the same idea here. It can be really useful to be able to isolate those ions that are doing things and those ions that are not doing things and are staying in solution. So what you can do is just really cancel or ignore those ions that don't interact. So for example, right, we could just say, oh gosh, look, these exist on both sides of that equation. So all that's really happening is that we have, a red dot. Wait, I canceled the wrong thing, didn't I? Oh God, I did. Oh no. Undo. Sorry guys. Coming back. Okay, here we go. We can't cancel a purple. We have to cancel a red and a blue. There we go. Oh, that's so much better. So what we see is that all that's really going on is we have got a purple dot, otherwise known as a silver ion, and it's going to react with a green dot, otherwise known as a chlorine ion, right? And they are going to make a silver chloride that is connected and ends up, being something kind of different, right? So one of those plus one of those makes that. That's all that's actually going on in that beaker. The other stuff, it's just chilling. It's just hanging out, okay? Let's look back at this picture. If it's aqueous, they are not together. So another way we can do this, right, we've been working on those models, but another way we can do this is with our chemical equations, and that's using something called ionic and net ionic equations. So the first one we want to look at is the full ionic equation. This is, when I just say ionic equation, I mean full or complete, like the whole thing, right? Net ionic is something different, and we'll look at that in a second. So if we want to write out a full or complete ionic equation, we are basically just going to take all of those aqueous solutions, and write out all those separate ions, right? So all we're doing is saying, hey, I understand that if it is aqueous, so let's not write them together. Let's write them as separate ions. This is your full ionic equation. Notice on the right-hand side, though, right, that silver chloride is in fact still together, right? That it comes together. It's a different thing. It's a solid. So again, this is showing exactly what you would see in the beaker, kind of just like that beaker model does. So the next thing is to do a net ionic equation, and the net ionic equation is what's going to show what we looked at with the model on the last slide, right? What's really happening. Let's ignore all the extra junk. So get rid of those ions that don't participate. Cancel them, if you want to think of it that way. So again, there's that full ionic equation, and if I want to go through and cancel some stuff out, right, I'm going to come and I'm going to say, okay, what exists on both sides? Well, I have an NO3 minus on both sides. I have a K plus on both sides. No, everything else is different, right? The left side has aqueous silver and chloride, and the right side has a solid silver chloride. They are fundamentally different. So then, right, we can just look at that and say, okay, check it out. What's actually happening? Here we go. It's the silver ion and the chloride ion. They are coming together to make solid silver chloride. The other ions are just swimming around in solution. They are not actually participating in any chemistry. Okay? All right. So let's work through a whole problem. I'd love it if you went through and just kind of worked as I go and paused so that you can work it out and then see if you get the answer. That's why I kind of pieced it out this way. So I'm just going to walk through it. Again, please pause to take time to try each step. So for the first part, all you're going to do is create that full and balanced equation, right? So we have copper chloride and lithium phosphate. And if oh, come on, let me do it. Don't do it. Oh, no. Shoot. Okay, hang on. Give me 30 seconds here. I just want this. Dang it. This wasn't supposed to do this. Okay, let's ungroup all of that. Go away, go away, go away. Just want you. Nope, I don't want you. I just want you. That's all I want. I don't want you. There we go. No. Okay. I'm so sorry, guys. This is lame. All right. Come on. There we go. Okay, thank God. All right. So, sorry about that. Alrighty. So now, let me just get this guy and kill that and kill that. Good. Okay, no, I just want you. Urgh. Sorry, guys. Okay, here we go. I wanted this to go over the other stuff, but there you go. So there's our equation. I really apologize. Once we balance it out, you see that your copper phosphate's going to be your solid, and it's kind of a larger equation. You've got, 3 in front of the copper chloride, a 6 in front of the lithium, 2 in front of, on, right? So it's balanced. There's a bunch of more stuff going on. It should make us a much more complex problem to work with. So for our beaker model, let's hope I can actually do this without ruining everything. There we go. There we go. For our beaker model, hang on. That's better. You can see I've drawn in all our particles. They're all there. And on the left-hand side, everything's floating around in solution. And on the right-hand side, everything's in solution except that, what do we have? The copper phosphate down floating at the bottom. Okay. Then you're going to write that full ionic equation. So I wanted us to do all these different steps. I'm not going to actually have you cancel anything in the beaker model here. I don't think that's really useful. It's just nice to kind of get the visual with that. But if we look down here, we can see there's our full ionic equation. So I just wrote out all of the ions. Do not forget to include the charges on the ions. Don't forget to include those state symbols. It's annoying and monotonous and long and drawn out, but you got to do it. Okay, then simplify and get that net ionic equation. So if I clean up this guy, we see, once we cancel, I guess I should have done that first, but right, here's my answer. But if I cancel, I'm going to say, okay, I've got 6 chlorides here, 6 chlorides there, 6 lithiums here, 6 lithiums there. Nothing else gets to cancel, right? The copper phosphate solid is different than the copper ions and the phosphate ions. So that becomes our net ionic equation, the copper and the phosphate ion to make copper phosphate. And we can call the lithium and the chloride spectator ions. That is their official name. If we were in class, I would do this whole song and dance about how the spectator ions are kind of like a wingman, right? So let's imagine here the lithium and the chlorine. They both are super sociable, right? They are just hanging out, chatting to whoever. Like, they do not have a problem going out and chilling at a party and making friends, right? But they each have a friend, and each of their friends are just really quiet. They're kind of wallflowers, right? So the lithium comes in with their friend phosphate, and the chloride, comes in with its friend copper, and like they're going to a party, right? So it's kind of like those sociable ions, the spectator ions, bring their shy, quiet buddies to the party and introduce them, right? Or just get them there, getting them into that solution, to that party, so that that copper ion and that phosphate ion can meet each other and then be like, oh my gosh, we're the best friends ever. We never want to let go of each other. And that's then when you obviously see that solid forming, right? Because we can't just ignore the fact that the lithium and the chloride are there, because they are, right? We've talked about this before. You cannot just have a beaker full of one kind of ion. You have to have that partner. You have to have that neutral compound. So without the lithium and the chloride, none of this could have happened, because the copper and the phosphate would have never gotten into that beaker in the first place. They needed a partner to get them there that would be aqueous, so that they could dissolve and find each other and then form their solid. Okay? All right. Moving forward, or not, I guess I didn't have anything there. All right, so let's try adding some of our math. This will be the next step. I'm going to put in a little activity that I want you to do that'll have you kind of move a little more in this direction. And then next week is when we jump back in head first into rocking our chem math. So let's get warmed up, okay? So here, let's just add some math. So if I mix 2 moles of my silver nitrate with 2 moles of my calcium chloride, what will the total number of moles of ions be in that solution after the reaction happens? Okay, so take a minute, pause it, try to work this out. Recognize I'm saying, okay, you have 2 moles of one, 2 moles of the other. We recognize they're both going to be dissolved, but then 1 ion from each of those is going to partner up with that other one, right? And you're going to have some of those ions come out of solution, but some of them are going to stay there. So you're going to need to do a little bit of stoichiometry, or well, not quite yet, but dimensional analysis at least, to figure out ions from those compounds, and then just a little addition. So let me zoom us out of here, and I'll walk you through it, okay? So here I drew out my full ionic equation. I felt like this was going to be the most useful to me right now, right? I can see that all of the potassium and the nitrate are just staying in solution. They are my spectator ions here, and the silver and the chloride don't. They become a solid, right? This is just the first problem we worked on in this lesson today. So if in this situation, since we want to know about ions in solution, we don't care about the solid right now. We actually care about the ions this time, okay? So I'll do some math, right? If I know that I've got my 2 moles of potassium chloride, well, I know every 1 mole of potassium chloride has potassium chloride has 1 mole of potassium ion. Therefore, do some math, and I see that I have 2 moles of potassium ion. Same thing for the silver nitrate to get our nitrate ion, and then we see if we have 2 moles of potassium ion and 2 moles of nitrate ion, add them together, in that beaker we have a total of 4 moles of ions in that solution. Okay, so that's a pretty straightforward example. I'm definitely going to post a trickier one in a separate video that I'm going to put up on the lesson. I'll just get it up probably by tomorrow afternoon once you've all had a chance to kind of get into the zone. But I want to show you also and say, hey, check it out. A better question, and this is where we're moving forward to, and this is what the extra activity is going to get you towards, is we would want to know the concentration of those ions in solution. Again, working with a number of moles in practical senses is not very helpful. Just like we're going to use grams when we're in the lab, and we're going to use molarity for concentration when we're in the lab, because that's the way we're actually going to function, okay? So this would be a better question. What's the concentration? We would have to remember that concentration is molarity. Capital M is the shorthand for it, right? And that is number of moles of solute, so whatever it is we're talking about that's dissolved, per liter of that solution. So if we had a volume here, let's assume we had a liter, and I wanted to know concentration of ions. Again, shorthand for asking about concentration is those square brackets. I would say, okay, well, what's my number of moles of solute? The ions are my solute. They are what is dissolved. So I would have 4 moles of ions in my 1 liter of solution. Do the math, and I get a 4 molar, oh, I guess I should finish my label, a 4 molar solution of ions, okay? So that's kind of where we're going with this, and then we'll take it into full stoichiometry with reactions after we get back into math next week. All right, so that's it for now. Please try to dig in to this stuff. I've got practice problems and keys posted. I've got a little FET going up to have you play around a little more with this idea of concentration. Really just engage with that to the depth that it is most useful to you. I just really want you guys to have a handle on what are we talking about with concentration. And yeah, and I'll put up a trickier question a little later in the week that we can look at when we do our live lesson. All right, hope to see you all soon. Bye-bye.